Single turbo. The most common turbocharger setup found in modern vehicles. A single turbo uses exhaust gases from the engine to spin a turbine wheel, which in turn drives a compressor wheel that forces more air into the engine. More air means more fuel can be burnt, and more fuel means more power. The concept was developed in the early 20th century with early applications in aircraft engines before eventually finding its way into passenger cars and trucks. A single turbo is simple, relatively inexpensive, and can be tuned to produce a wide range of power outputs depending on the size of the unit. Smaller turbos respond quickly and suit daily driving, while larger ones take longer to spool up but deliver far more power at higher engine speeds. That delay in response is commonly known as turbo lag, and it remains the main trade-off with any single turbo setup. Twin turbo. A twin turbo system uses two turbochargers instead of one, and this arrangement can be configured in several different ways depending on what the engineer is trying to achieve. The most common version runs both turbos in parallel, with each unit handling half of the engine's cylinders. This keeps the individual turbos smaller and lighter, which means they spool up faster and reduce lag considerably. Another arrangement runs the turbos in sequence, where a small turbo handles low engine speeds and a larger one takes over as revs climb. Sequential twin-turbo systems are more complex and expensive to build, but they provide strong response across a much wider power band. Vehicles like the Toyota Supra and various Porsche models have used sequential twin-turbo setups to deliver smooth, consistent power from low revs all the way to the top of the rev range. Bi-turbo. A bi-turbo system is often used interchangeably with the term twin turbo, but in many cases it refers specifically to a setup where each bank of a V-shaped engine has its own dedicated turbocharger. In a V6 or V8 engine, the cylinders are arranged in two rows, and feeding exhaust from both banks into a single turbo creates a longer, less efficient path. By placing one turbo on each bank, the exhaust gases travel a much shorter distance before reaching the turbine. This improves response and reduces heat loss along the way. Mercedes-Benz and BMW have both used bi-turbo configurations extensively in their performance and luxury lineups, often pairing them with inline-6 or V8 engines to achieve a balance between refinement and power output. Twin-scroll turbo. A twin-scroll turbo is a single turbocharger with an important internal modification. The exhaust housing is divided into two separate channels or scrolls that feed exhaust gases into the turbine wheel from different directions. The reason this matters comes down to exhaust pulse timing. In a standard single turbo, exhaust pulses from different cylinders can interfere with each other as they travel toward the turbine, which reduces efficiency. By separating the pulses into two distinct scrolls, each pulse arrives with more energy and pushes the turbine more effectively. The result is faster spool up, less lag, and better overall efficiency without the added cost or complexity of running two separate turbines. Many modern performance engines from manufacturers like BMW and Subaru have adopted twin-scroll technology as a cost-effective way to improve response. Variable geometry turbo. A variable geometry turbo, often referred to as a VGT, uses a set of movable vanes inside the turbine housing that can change their angle depending on engine conditions. At low engine speeds, the vanes close partially to create a narrower passage, which accelerates the exhaust gas and spins the turbine quickly despite the limited flow. As engine speed and exhaust volume increase, the vanes open to allow more gas through and prevent the turbine from overspeeding. This adaptability gives a variable geometry turbo the ability to respond well at low revs while still flowing enough air at high revs to maintain power. The technology was pioneered largely in diesel engines, where it became standard equipment in many commercial and passenger vehicles. Porsche later applied a petrol-compatible version of the 997 generation 911 turbo, marking a significant development in bringing VGT technology to high-performance gasoline engines. Electric turbo. An electric turbo uses an electric motor to assist or entirely replace the exhaust-driven spinning of a traditional turbocharger. The fundamental challenge with any conventional turbo is that it relies on exhaust energy that only becomes sufficient at higher engine loads. An electric motor can spin the compressor wheel almost instantly, regardless of what the engine is doing. In some hybrid applications, the electric motor sits between the compressor and turbine wheels and can either add rotational force during low-speed conditions or recover energy from the exhaust stream and feed it back into the vehicle's electrical system. Audi introduced a production version of this technology in their SQ7 diesel, using a 48-volt electrical system to power an additional electric compressor working alongside conventional turbos. Formula One has also used a form of electrically assisted turbocharging for years, where the motor generator unit on the turboshaft plays a central role in the car's energy recovery system. Compound turbo. A compound turbo system uses two turbochargers arranged in series, where one feeds compressed air into the other. The first turbo, known as the low-pressure stage, compresses incoming air before passing it to a second high-pressure turbo that compresses it further. The combined effect produces a much higher level of boost than either turbo could achieve alone. The downside is added complexity, the need for an intercooler between the two stages to manage heat, and significant packaging challenges. Some high-performance diesel pickup trucks have used compound setups to push output figures well beyond what a conventional single or twin arrangement could reliably sustain. Centrifugal supercharger with turbo characteristics. A centrifugal supercharger operates on the same aerodynamic principles as a turbocharger, but draws its power from a belt connected to the engine's crankshaft rather than the exhaust stream. Like a turbo, it uses an impeller spinning at very high speed to compress incoming air. Because output increases with shaft speed, a centrifugal supercharger produces relatively little boost at low revs and builds pressure as engine speed climbs. This behavior sets it apart from Roots type and screw superchargers, which deliver boost more immediately across the rev range. The centrifugal design is more efficient at high speeds and generates less heat than other supercharger types, making it a popular choice for street performance builds where packaging space is limited and high RPM power is the goal. Water injection turbo system. A water injection turbo system is not a different type of turbo, but rather a supplementary system used alongside a forced induction setup to manage intake temperatures. When air is compressed by a turbocharger, it heats up considerably, and hot air is less dense and more prone to causing detonation inside the engine. By injecting a fine mist of water or a water methanol mixture into the intake tract, the system absorbs heat through evaporation and lowers the charge temperature significantly. This allows the engine to run more boost pressure or more ignition advance without damaging itself, which translates directly into more power from the same turbo setup. BMW reintroduced this technology in the M4 GTS and later the M4 competition, demonstrating that a well-engineered water injection system can extract meaningful performance without requiring larger or more complex hardware.